Hello and welcome to my class. If you need to write to me asking any questions about what you're seeing here, you can write to me at this address, Pascal Class, all lowercase, at heyman.us. I also have a help website available. Case is important, heyman.us/pascalclass/helpfiles.html. First of all, I would like to start with a relatively simple program, but there's some concepts here that we need to discuss. It has an ORD function in it. This is a standard Pascal function that returns the numeric value of a character, the ASCII numeric value, in the case of ASCII machines. Almost all machines that you would use are going to be ASCII except for possibly IBM mainframes. ORD is short for ordinal, and one of the dictionary definitions is a noun, a number that indicates the position of an item in a series, such as first, second, third, 25th, and such. For the record, the CHR function is the inverse of the ORD function. So a decimal value will return an ASCII character as long as it is between 0 and 255, but only values 0 through 127 are printable. I can show this to you. Here we are using a for loop to go through all the uppercase characters. If you take ORD of A, should give you a value 65. And if you look at an ASCII chart, and I just downloaded this somewhere off the internet, the capital letter A is going to return a decimal 65. All the way through Z, which should return a decimal 90. So we're basically saying for I equals 65, 290, do, rightlen, first the char of I, which should start at 65, and then the numeric value of the char of I, and then taking the ORD of that, which should give us back the letter A. So if we go ahead and run this, let's compile it first. It did exactly what I said it would. It starts out with 65, which is an A, 66, which is a B, all the way through Z, which is a ASCII value of 90, or a decimal value of 90, and it gives you the letter Z. Now in here we're doing something a little funky, something I haven't discussed, and it may be a little bit of a leap, but we have played with strings before, but a string is really what is called an array. It's an array of char. We can reference each character in that string by the string name and an index value, which needs to be of some form of integer. And that's what I'm doing here. You put the index value, the integer, which is I have named I, into square brackets after the name of the string or the name of the array. And that should allow us to print out individual characters. And by taking the ord of it, we're getting a number value. And here I'm saying if the value of that character is greater than 65 or less than 90, then we're going to add a value which should make it lowercase. That's what this math statement does. We're converting all uppercase into lowercase because it doesn't make sense to mix the two. This is what is called a magic word program, which it basically sums up the positional value of all the letters together. It's a cute little toy program. Nothing special. You may see other programs that do something similar. And this is what sums up the value. Actually, these two statements. And then finally, we write out the value of the prints out the value of the sum of all the letters of the string. A better example would be, let's just use the letter AB. Which should give us 3, which it does. AC is 4. As you can see, case doesn't matter. Again, if you have any questions about this, you can write to me. Moving along, we're going to change directions completely. And look at this example 6, which is a program to produce the number factorial. Basically, factorial of a specific number is multiplying all the numbers 1 through that number together. All have to be whole numbers, and it's used in statistics quite a bit. Now here the type is integer. And we know the limitations of integer being that you can't have a value above 32,767. And it turns out that that factorial number builds very quickly. When you start multiplying that many numbers together, even small numbers, it builds fairly quickly. And the largest factorial that you can have with just an integer type is 7, I believe. One should return 1. Two would be 2. 3 would be 6. 4 should be about 24. And 5 is 120. And if you go up to 7, that's 5,040. And if you multiply 8 times 5,040, you know it's going to be more than 30-some thousand. Factorial is used mostly in statistics. It's used enough that it's on a calculator. In fact, it's on almost all scientific calculators. Every scientific calculator I have seen has had a factorial function. It's usually the exclamation point, and if we push 5 and then exclam and push the equals, it's 120. If you do 8 exclam, which is more than 32,767, so it overflows. And if you try it here, you're going to get a negative number, which you know is an overflow. The next example I have has only changed one thing in the program. We've gone to a long int, and you can get a much larger factorial value in a long int, but you can overflow a long int quite easily too. I don't remember off the top of my head how large this can be. I think it's around 15 or 16. All right, it overflowed at factorial 17. And if we came over here, typed in 17, and pushed the factorial button, it's 3.5 times 10 to the 14th, which is a very large number. You can also do factorials with floats, and that's what that is there. That's a float. It's not that different. You're basically saving the value in a floating point value, but you can still multiply the integers with a floating point, giving a result of a floating point. That's the only real difference here. This does run. And as you can see, it did not overflow. In a lot of cases, using floats is safer than using integers. The problem with using division specifically with integers is you cannot have a partial return. You cannot have a non-whole number. It gives you the minimum whole number and throws away the rest. And Nicholas Wirth thought that integer math was different enough that he gave a different division operand than floating point. And the div in Pascal is divide integers. While you, in a floating point, you would just use the right-hand slash. It's going to give you a result of a whole number. You can find the remainder by using the mod operand, which gives you the remainder of a division. In 7b here, I show the divide, which is this statement, and the remainder, which uses the mod operand. Right here. The mod and the div have been with Pascal since Nicholas Wirth released it in about 1970. We can go ahead and test this. This gets the a parameter from the command line. This is a little bit interesting since we're for looping through the series of operands up here at the command line. Param count gives you the number of parameters you've got. The program knows that 1 is the beginning point, and param count will be the ending point. And you almost grab it like an array, except you use the round parentheses here. And the result should be 15, with an average of 3, and there's no remainder here. But if we add 1, it says the average is still 3, but it now has a remainder of 3. Okay. Here we have written a tiny little program to add some constants together and then multiply it by another constant. We're adding 1.5 times 2.8. And it says we should get 34.16. Let's see if we do. And no, we didn't. And there's a very similar program here, except here we divide. And let's see what the answer should be there. It says we should get 4.35. This is the wrong one. And as you can see, we did not get that. This is the PEMDAS reaching out and biting us. The order of execution of instructions is multiplication and division occur before addition. In fact, the order is parentheses, exponents, multiplication and division. Actually, I believe it's division and multiplication. And then addition and subtraction. So addition and subtraction occurs last. So in this case, this part would occur first, then followed by this. And that gets us into trouble. We can fix this very easily. By using parentheses. Here I have put the parentheses around the additions so they occur first, and then it multiplies. And same thing here with the division. Basically, I would overdo using parentheses because that will keep you out of trouble. And finally, I want to discuss logarithms. Logarithms are very important to computer science. You can't get square roots or raising something to a power in Pascal without using logarithms. There are some languages out there that do something like use a double asterisk to raise something to a power. They're just doing logarithms behind the scene and hiding it from you. Logarithms, often just called logs, are basically exponents. Exponents have some very interesting properties. If we add two exponents of the same base number together, the result is the same as multiplying the two original numbers. An example here is 8 times 16 equals 128. But 8 equals 2 raised to the third power, and 16 equals 2 to the fourth power. So if you take 2 raised to the power of 3 plus 4, which equals 7, that also equals 128. Square roots are the square root of let's say, of 25 is 25 raised to the 1/2, which is 5. If you take the cube root, you divide by 3. So around 1600, a real nut job by the name of John Napier, you can find a wiki page about him, got the brilliant idea that any real positive number can be represented as an exponent of a specific base number. In computer science, we use E as the base, and it's a funky, irrational number, and humans aren't comfortable with it, but it becomes sort of a black box. People like to use base 10 logarithms, everybody but mathematicians, and mathematicians got their way when computer science developed. So this little program here takes the base as the first parameter and the power as the second power. To get the logarithm of a specific number, you take the ln function, which gives you the natural log, and then you multiply it by a power, and then you have to take the exp function to get all of that back into a real number that isn't an exponent. So if we try doing this, and we take 2 and raise it to the third power, that should be 8. Also, if we take 25 and raise it to the half power, we should get the square root, which is 5. This works with non-whole numbers also. So you could take 5 and raise it to pi fairly easily. You'll get a funky number, but it's doable. And if you did that on a calculator, you should get something very similar. Fairly close. It's probably they may be using less than double length floats, which I have used here. Now, that's all fine and very well, but how is this going to be really useful to you? So I wrote a useful little program. We'll get to that in a minute. I'm not going to say this is better, but there is a power function in Pascal that allows you to raise a value and a power, and it hides what's going on behind the scenes. What's going on behind the scenes is it's calling ln and exp for you. And it does work, but you have to include the math library. And I believe that I have this already compiled. No, I don't. It did the same thing as what we did up here, and you got the same response. It's your choice how you do things here. The power function is convenient, but I kind of like knowing how things work. And that is an example of the previous one is how things are actually happening. And this is just a wrapper. It's not checking these numbers to see if they're valid. If you try to raise a negative value to a power, that program's going to crash. Oh, I did that wrong. I tried to take the log of a negative value, and logarithms have to be, when you take a log of something, it has to be a positive value. So you really need to check to see if it is a positive number. Or take the absolute value of it and then know later if you're trying to take a negative number or not. Even though taking a square root or something of a negative number is not valid. A mathematician will tell you that. Because the response should be an imaginary number. And finally, I am going to look at one more program. When banks figure loan amounts, they know what the interest rate is, and they use logarithms to, or at least power values, to calculate the amortization table. And it's all based on this formula here. And since Pascal does not have an exponent operand, you have to use these functions. It makes it a little more complex. In COBOL, we would have typed in something very similar to that in a compute statement, and it would have been nice and pretty. In Pascal, you have to jump through a few more hoops. It is doable in Pascal, and I have done it here. the program is going to expect some values. First is going to be the amount borrowed. Second parameter is going to be the interest rate. And the third is going to be the number of periods. This program is going to assume the periods are months. It wants a date when the money was borrowed. And it needs to be in year, 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 month, month, day, day format. And finally, parameter 5 is 0 to print to the screen, 1 to print to the system printer. To make this a little easier to understand, I have done the top part of the formula and as one variable, the bottom part as another variable. Since the interest rate, which is going to come in like 6.5 for the interest rate, we really need to divide that by 100 since it would be 0.065, and by 12 to get it into periods, because we have to get the interest rate per period. You end up dividing by 1200. So in here I do have where I'm calculating the 1 plus R to N, basically this part, into the top variable, and the bottom is going to be the 1 plus R to N minus 1, which is this part. I can divide those two and multiply it by principal. Which is right here, and that's going to calculate the payment, the monthly payment, and then it's going to loop through and calculate the principal paid and the interest paid and such. So we can compile this. That was a little bigger program, and it took a little longer. It took 0.7 seconds, and normally the programs we've been compiling is 0.0 or 0.1 seconds. And I think we need a little bigger screen here. So let's go look at what the parameters need to be. First parameter is the amount borrowed. Let's say we're going to borrow $100,000. So I'm going to just put in 1E5. That's 1 times 10 to the 5th. The interest rate, let's put 6.5%. And let's make it a 30-year, which is 360 payments. And we need to put the year in. The principal due. That would be your, if you wanted to pay it off early, value. And over 30 years, it would pay down to zero. If you have any questions about this, you can always write to me. I realize this program is more complex. And maybe I can explain it in more detail if you need that. Well, that's the end of this session, and good luck. Thank you.